Okay, let's get going. Optimal control theory. So, this is perhaps one of the current passions in magnetic resonance. An increasing number of papers coming out on the subject, primarily to do with the fact that greater and greater requirements are being put on NMR instruments without there being any major order of magnitude breakthroughs in the capability of the instruments. So we require greater and greater excitation bandwidths with lower and lower radio frequency budgets, better and better MRI images with the same legal requirements on the total power deposition in the patient body, higher and higher sensitivity, better and better excitation, faster and faster transfer of magnetization from one place to another, with essentially up to cosmetic improvements the same instruments. And so one of the important tasks is how do we do a better job, particularly in heterogeneous, inhomogeneous, and otherwise distributed spin systems. And as a part of it, how do we do better and better job of just simply moving the quantum state around the system, from single magnetization back and so on. So that's the topic of optimal control theory, how to do the most in the least amount of time with the least amount of effort. So a good example of such a problem is if we have 2 points on a map, an A and a B, and we have a herd of sheep parked at point A, and we need them moved to some point in B. Now we have one dog to do that, which just runs around the sheep and barks and bites, but every sheep in the herd would have slightly different height, slightly different mass, slightly different speed, and each and every sheep will trace its own course on what potentially could be a heterogeneous terrain. So it will actually even move at a different rate, all other things being equal. So how do we, having one dog that runs around them and barks at them occasionally, transfer all the sheep from point A to point B with the maximum accuracy in the least possible amount of time, with the least expenditure of effort by the dog? So, classical optimal control problem. So, consider a spherical shape in vacuum, and as a first approximation, we will assume it to be a two-level system and therefore representable as a spin. Let us say we have our initial condition, psi 0, and we have our destination, sigma, where we want our system to be. So, initial conditions of start, and that's the destination. Well, we do know how to score whether or not the system has got in there. We can just take a scalar product and create a quantity J, which would be the real part of the overlap between the sigma and the psi at the end of our trajectory. Now, if psi at the end is exactly the same as sigma, this would be equal to 1. And if psi is different, this would be less than 1, because both functions are normalized. And we take the real part of it just to make sure that not only the function itself, the density part of the function are right in there, but also the phase is correct at the end of the trajectory, because if they overlap in the correct phase, this would be a real number. And this real also gets rid of quite a few quirks of the theory of optimization, which it tends to develop over complex fields. So what we will now do is just write down the Schrödinger equation for the evolution of the quantum system with some time-dependent Hamiltonian and get it going. So, in our Hamiltonian, which will be time-dependent, we will identify two parts. One would be called H0, as I'll stick to 0 here. And this is the part of the Hamiltonian that we cannot control. Things like J-couplings, things like chemical shifts, and other such things that do not allow straightforward instrumental influence. So this is known in the trade as the drift. These are the things that we do not control. But we also have things that we do control. So there will be a bunch of operators in magnetic resonance, typically rate of frequency, some over n, some coefficients, Cn, which could be time dependent because our instrument can alter the magnitudes of the corresponding electromagnetic fields, and then operators corresponding to those fields. Now, this part is called the control part. The operators in question are called the control operators, or in the jargon just controls. And Cn are the steering inputs in the old-fashioned language, and the control coefficients, as we call them in magnetic resonance. So we would like to find such a sequence of control coefficients as would take our system from some initial condition, say a singlet, to some final state, say a magnetization, subject to various constraints on these coefficients. And the constraints could be many. Our instrument is not perfectly well tuned, so there will be some frequencies that it cannot reproduce and others that it can. So, for example, there would be a cutoff on the maximum frequencies that these Cs can contain. Our instrument doesn't have infinite power, and so there would be a constraint on the maximum amplitude that these coefficients can have. The duty cycles of amplifiers are finite, and so the total integrated amplitude of these things can be capped. We would want, in some cases, for them to decay smoothly and rise smoothly at the beginning and end of the control sequence, so we don't have any jitter. And so there will be various constraints placed on that, which we do need to account for. So as well as the fidelity here, which we need to maximize, there will also be costs which we need to minimize. And the costs will be related to the extent that our control sequence satisfies our various constraints. So I've listed the various constraints in your handout, and at the end of it there was, and I think there is, a slide called penalty functions. So take a look at it. It lists the various typical penalties that we can have. And so let us now just write down the Schrödinger equation with that Hamiltonian and plug it into the expression of our fidelity. So our wave function at time t would be the result of time propagation under this time-dependent Hamiltonian from the initial condition psi 0. Now, those of you who have been through time-dependent quantum mechanics would remember that under time-dependent Hamiltonians, the propagation is described by the so-called time-ordered exponential, or equivalently, if we can just slice them into small enough piecewise constant little slices, we can just sequentially propagate it through those slices under constant Hamiltonian. But strictly speaking, it's xo, the time-ordered exponential, minus I integral from 0 to t, h over t dt, applied to psi 0. Now, I would remind you that time order means that it's not as simple as just integrating the thing and then taking the exponential of it. It's more of a placeholder for a much more complicated object. So we plug this into here, and so that would be ordered exponential minus I 0 to t, h naught plus the sum O of n, C n T H n T, and then multiplied into psi 0. Now, we need to take the scalar product of the resulting wave function with sigma, and so when we write down our final J, the fidelity as it's called, its reciprocal is jokingly known as infidelity. So sigma x0 or x ordered minus I integral to t, these brackets, t sine 0. So this is the expression that we would like to make as big as possible. Now, typically, because we also need to minimize the costs, we subtract the costs from it. Now, these costs can have rather complicated expressions. I would not dwell on this much. They are given at the end of your handout, the various expressions for them. They are typically just related, let's say, the total energy cost is the sum of absolute squares of these coefficients. It has straightforward derivatives. So, in a way, this part, from the numerical optimization perspective, is nearly trivial. What is complicated, and what we will be dealing with today, is the quantum mechanical part of it here. So, this J is, from what we had written, a functional, and the only thing that really is variable here that J depends upon is the set of these coefficients. Yeah, so it could be, usually for a single channel NMR experiment, there are two terms in here. One corresponds to Lx and the other to Ly, so the two coefficients in front of those operators. So our J is in fact a functional of this Cn of t. And we would like to find a maximum of J on the space of all such functions. Now, this, in the most general case, is a variational calculus problem. We need to take a functional variation of this with respect to these coefficients, and then use that variation as a gradient in the minimization procedure. But typically, we don't actually need that. Our instruments output this as a discrete time sequence anyway. Yeah? In our amplifier, it wouldn't output a continuous function, it will just output a digitally synthesized waveform, which is, in some instruments or in others simply can be made, a piecewise constant function. And so, we don't need to go through the functional analysis here. If you have appetite for Grotov type methods, I'll go through them at the next lecture. What we typically have in practice is the following. If we plot our coefficient Cn of t as a function of time, the ideal function would be continuous, but the practical situation is that we've got these finite steps. And so on. And within each step, assuming these steps are sufficiently fine, we can assume the coefficient to be a constant. And so this is, say, t1, t2, t3, and so on, tk, all the way to t, let's say, n. And so these continuous functions just become vectors, finite dimensional, and the functional optimization problem is transformed into simply a nonlinear optimization problem with respect to a hell of a lot of variables. So, in the actual reality, what we have is J is a function, but of just a bunch of numbers. So, C and K, Z control sequences. So we can rewrite that now in a vector language with discretized coefficients, and one immediate benefit that we get from doing that is the fact that the time-ordered exponential for a piecewise constant Hamiltonian splits into a product of individual slices, which are then easy to compute. And this is how we do our magnetic resonance simulations usually. In 10 years of doing these theories, I've yet to see a single paper that actually computed this crocodile and used it in any way whatsoever. It's always time slice, except in very highbrow analytical simulation things. So, our time-ordered exponential of minus I integral 0 to t h naught plus a sum of n c n of t k, or equivalently just c n k h n t t becomes sliced, and we will just keep the sizes of these slices, the lengths of the slices, the same. It is to do with the fact that it's much more convenient later when we start differentiating these exponentials to have constant time slices. It's not strictly speaking necessary, it's just a bit more convenient for practical purposes. So this becomes a product, again an ordered product because they needn't necessarily commute, of simple exponentials minus I h naught plus a sum over n c n k h n delta t. And these things are quite straightforward to compute. They're just individual slices, and we will denote them UK. So it will be a product of UK. Time propagators for the kth point in time. So from this, our wave function at the kth time step becomes just a product UK, UK minus 1, and so on, U1 psi 0. A bunch of these operators, where each individual UK is this matrix exponential here. And so we can now write our fidelity in terms of these UKs, and it would suggest us a method of running the numerical minimization for this in order to get to our target and to find our control sequences that we need to plug into the instrument to achieve that target. So our J is now, it's still the real part, it's still projected onto the destination state, but un minus 1, un minus 2, and so on, u2, u1, psi 0. And these are just slice probabilities, where each individual UK is, as per the above, an exponential of minus I h naught plus the sum over all the controls, the amplitudes of those controls at the current time point, times the control operators, times the length of the kth time slice. Okay, so we've now discretized the system. So what we need to calculate in order to run our numerical minimization is the gradient of J with respect to the amplitudes of these control sequences. In other words, the thing that we require is dj by dc and k for every n and for every k. That would be the gradient, and then we can just take a step down that gradient to use a straightforward gradient descent. We can use conjugate gradients to take into account limited second order information, or quasi-Newton to be a bit more sophisticated, or if we are in fact lucky enough to be able to get second derivatives of this thing in a cheap way, which nobody so far has been properly able to, then we can use straight Newton methods, and then they converge really, really rapidly. Now it so happens in this art that the first derivatives, as we shall see in a moment, are remarkably cheap. Now, from the naive view at the problem, one would think, well, yes, we can do it, for example, with finite differences. We can just calculate j for a given c and k, increment it a little bit, recalculate j, subtract the 2, divide by the increment, and that would be the derivative. Of course, if we have several hundred points in time and 2 controls, that would mean several hundred complete simulations of the system per minimization step, and that's just far too much. Now, one of the key advantages of the great method that I will describe, and the reference to the original paper by the Munich group is given in your handout, is the fact that, in fact, once you think about how to compute these things, it turns out that no matter how many steps you have in time, or how many controls, you still need just 2 simulations, one forward and one backwards, to calculate the entire gradient. And so it's considerably cheaper than a brute force simulation, or even a casual look would actually suggest. So let's see what this thing is and how it can be calculated. If we look very carefully at this UK, we would notice that out of these terms, un minus 1, and so on, this index occurs only in the coefficient, that is the control magnitude. And so the only propagator out of this entire set that actually depends on ck is the case one somewhere here. These ones do not. This one depends on Cn big, this one depends on Cn minus 1, and so for the purposes of differentiation, of course, because these individual points in time are independent, they're just constants. And so when we differentiate j with respect to ck, it just, sigma doesn't depend on it, it's fixed, this doesn't depend on it, this doesn't depend on it, this doesn't depend on it, something in the middle here does, and the rest of it doesn't. And so when we write out neatly what it is that we actually require, it turns out, so I will write it out very carefully, so sigma un minus 1, uk plus 1, uk minus 1, u2, u1, psi 0. And then I will write it underneath again, just for schematic illustration purposes, un minus 1, uk plus 1, uk minus 1, and so on, u2, u1, sign up. So when we differentiate j with respect to the control amplitude at case point, only this term gets differentiated. So instead of this term, what we have in the middle is d by dc and k of that uk. And it replaces the propagator. And so what it turns out we need to do is we need to run the simulation forward, this part, up to the point immediately before the point that we're differentiating. So forward from source. Yeah, this is just the usual simulation, first time step to psi 0, second time step to the result, and so on. And then we need also to propagate the destination state backward up to the point immediately succeeding, the one we are differentiating, the destination, backwards. And then this wave function and this wave function, we need to calculate the corresponding matrix element with that derivative. And that would be the dj by dcn k. Now, if we now calculate the derivative with respect to the k plus 1, the entire picture shifts. And you see, it's much easier to just run one calculation forward completely, run another calculation backward completely, and then just take these scalar products with the derivatives of the matrix exponential. So the problem therefore reduces to just computing the derivative of the slice propagator, and therefore the derivative of a matrix exponential, or more precisely and more efficiently from the computational perspective, we don't actually compute the derivative of a matrix exponential, we compute the derivative of the action of a matrix exponential on a vector. As we'll see in a moment, that's a considerably cheaper thing to calculate. It's actually quadratic in time and resources rather than cubic, as most matrix operations are. Okay, matrix exponential derivatives. Let us make a shorthand. I will denote the total Hamiltonian at time slice k with hk, and it will be h naught our drift plus our controls. The control amplitude of n's control at k's step times the n's control operator. So we are looking to calculate now d by dc and k of the exponential of this thing. So x minus I h k delta t. There are various ways of doing it, and we always must bear in mind that it's not the exponential itself we are calculating, but its action on a vector. Now, the difference may be subtle, but let me demonstrate it. Let's say we have a pretty high dimensional matrix, so maybe 1,000 by 1,000 or more. Spin Hamiltonians are always extremely sparse. So in a spin system that we typically would encounter, there will be a few dozen non-zeros per column. So matrix vector operations in such a setting are very, very cheap. So let's take a look at the following thing. So xa times av. So we exponentiate a matrix and multiply it into a vector. As we know, that's the Taylor series of the exponential 0 to infinity, a to the n over n factorial multiplied into v. Now we can do it in one way by multiplying matrices. However, the cost of matrix-matrix multiplication is order n cubed. If you have some really, really latest algebraic technology in your computer, I think the asymptotic scaling is n to 2.6 or something like that, but it wouldn't become quadratic. Yeah? It is an expensive procedure, matrix-matrix multiplication. What we could alternatively do is to make sure that this A matrix is properly scaled, so we scale our time step, right, so that the Taylor series converges, as it usually does for a well-scaled matrix in about 17 iterations to machine precision. And we can do the following. We can say it's n from 0 to infinity 1 over n factorial, A times A times A times A, and so on, A, B. You see, when we multiply this matrix into a vector, it's a matrix vector multiplication. It goes as O n squared, and in sparse cases it goes as O n. The result is a vector. If we multiply A into it again, it's again O n squared. For well-scaled A's, we're talking 10 to 20 iterations of Taylor at most. And so we've got 20 times O(n) squared compared to O(n) cubed, and if the matrix is 1,000 by 1,000, 10,000 by 10,000, we are saving 2, 3, or 3 orders of magnitude in the runtime. So big, big difference. So the general family of such algorithms that do this are known as Krylov methods. It can be applied on top of Taylor, it can be applied on top of Chebyshev, any polynomial series in matrices, and it saves a huge amount of time. So when you look inside Spinach, at the optimal control module in there, we never actually compute these exponential derivatives. We always compute the actions by these derivatives on the vectors, because it is considerably cheaper. The other technicality in there is that once you've computed your forward calculation and the backward calculation, the task of computing this times the vector for every k, these tasks for each k are independent. And so there is a considerable scope for parallelization in there. So if you look at the k loop in Spinach, again you would see a par 4 in there. It is parallel, and with thousands of time points, as you often have, it can scale pretty well. But okay, so all of that having been said, I would not actually drag this vector in front of these expressions. I'll just carry them as if they were matrix operations, on the understanding that this is how they are actually implemented and should be implemented always. Okay, so, well, how do we calculate these derivatives? The biggest problem, of course, is the fact that Hn needn't commute with each other and needn't commute with H0. So the standard formula whereby we just take this thing in front and differentiate it with respect to ck just wouldn't work. Yeah, it implicitly assumes, if you look at it carefully, that those matrices commute, and they generally don't. So, well, one thing we could do is just use the Taylor series definition and then just differentiate the Taylor series, taking into account that non-commutation. So it would be d by c and k of the sum, let's call it m, the summation index 0 to infinity minus I delta t to the power m over m factorial, and then we've got h k to the power m. We take the derivative in, and that's a sum m0 to infinity minus I delta t power m over m factorial d by dc n of hk, 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 and so on, hk as mth power of. Well, product rule still applies, so a derivative of a product where every term does depend on ck is just a sum where in each term we differentiate one of these matrices and keep the rest of them there. So we get in the end a double sum, so 0 to infinity minus I delta t m factorial, and then another sum in here, L 0 to m, hk, 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 and so on. Now, the derivative of hk with respect to c and k, this dies. All of these terms except one also die, and so we are left with just the control operator. And then hk, hk, and this control operator occurs in position L in this thing. Well, it's okay, it works. When I implemented it in the code, it produced considerable improvement of various other approximations to this derivative. The biggest problem, of course, is a double sum. Yeah, we have to sum this up, and that's a lot of operations, and even if we have a vector here in front, multiplying all these enormous things eventually into that vector is a lot of multiplications. So double sum is quite inconvenient, and in practice this works, but this is very slow. An alternative to this is I will skip a very large amount of non-commutative matrix algebra in here. It turns out that you can rotate these summation indices. Now, who's familiar with summation index rotation? Not an obvious topic. So if we have two indices, so that would be index M and that would be index L, we go all the way to infinity in M, and we go only as far as actual M in L. So if this is 1, 2, 3, 4, 5, we'd have this sort of pattern in L and M. Now, at the moment, we are summing it. First, we sum the rows, and then inside we sum the columns. In principle, what we can do is, for example, sum it like this. It would still be the same sum, but then both indices in it would be infinite. So it's an infinite sum along each arrow, and there's an infinite number of arrows. So both sums here would be infinite. One would be over the L plus M, the other over L minus M, I seem to remember. And then this entire expression splits into a pair of disjoint Taylor series, which you can then actually return back into the analytical expression. That's a tedious procedure, so I'm skipping it. But the final result is what's known as Hausdorff series, except it isn't quite, so let's just call it a commutative series. So one Taylor series just collapses back into the original exponential, hk delta t, and the other one remains, but it's a commutator series. M0 to infinity minus I delta t to the power m over n factorial, and then we've got an n-fold nested commutator, hk h and control operator m times nested. And well, the advantage of this is there's just one sum, considerably easier on the computer. Don't need to worry about two convergence criteria instead of one, and other various things, but this is still not the optimal way of doing it. Again, implemented in Spinach, it's considerably better than this. It works, but still not the best way of doing it. I'm just listing it for historical reasons, and also perhaps to save you a considerable amount of time at trying to improve the code that's in there. So we've been through a considerable number of various dead ends, certainly in terms of speed, because of course analytically, in terms of giving the correct answer, these things are equivalent. Now, the other thing that one might be tempted to try is, of course, the finite difference stencils. I mean, what's the point dragging all of this enormous matrix algebra around if we can increment A a little bit computed with Krylov, you increment it a little bit computed with Krylov. Again, subtract, divide by the difference, and in principle we retain the matrix vector arithmetic advantage in there, and with a well-chosen finite difference, stencil might actually, not lose any accuracy. So the third way of doing that is by finite difference. We know that f prime of x is approximately equal to f of x plus delta x minus f of x divided by delta x plus O of delta x. I think delta x or delta x squared is here. I think it's squared. So first order accuracy. Even better, we can do that. F prime of x is approximately f of x plus delta x minus f of x minus delta x over 2 delta x. That has quadratic accuracy. So called delta x cubed error, so-called central finite difference stencil. And if you just Google it up, you will find a huge pile of these stencils, some better than others. Spinach implements the second order stencil because it has no costs compared to first order one, but better accuracy. And it also implements a central fourth order stencil, which has got both delta x to the fifth. In here, again, both work just fine, but the downside of them is they rather strain the double precision arithmetic. We are relying on small differences in here divided by small numbers. In many cases, the condition number of the various matrices involved here is not that impressive. That is, there's a huge spread in the eigenvalues. And if we are talking 4 orders of magnitude spread in the eigenvalues, the tiny increment in here, we are perilously close to the accuracy limits of double precision arithmetic. And so even though, again, all of these things are implemented and apparently work, I would not advise using them in practice, because for some hairy ill-defined problem with large spread in the Hamiltonian eigenvalues, you might just hit that limit on the accuracy of double precision. We've done our best. We choose delta x in a very intelligent way, based on the local machine epsilon and so on. But still, these things carry a health warning, simple as that. So the current favorite, and the method that is, on the one hand, as fast as finite difference, and on the other, as accurate as all of this matrix algebra, is known as the augmented matrix exponential technique. And it is given to you at one of the printed pages of the handout. The last one, I think. There. Proposed in our optimal control context by Sophie Shermer from Swansea, just last year here in Southampton, actually, at a conference that we organized. It relies on something that's sort of fairly magical property of matrix exponentials, namely that if you have an x A, B, C, 0, where A, B, and C are blocks of a matrix, then after quite a lot of mathematics, and there are papers dealing with how to do that in reasonable time, the exponential ends up being equal to the following thing. E A 1 minus S B. I should put hats on these things that are operators to distinguish a matrix from a scalar. E C S D S E to C and then 0. Well, you might reasonably ask, so what? And it turns out that this integral and this commutator series here are actually the same thing. If you sum up this commutator series very carefully, it actually sums into this integral. And so in a language that is more appropriate for optimal control theory, minus I H delta T, this is the total Hamiltonian, minus I H n delta T, that's the control operator, minus I H delta T. This exponentiates into x minus I H delta T, d by dc. And so that coefficient at that time step, I just put the time indices here, k, c, and k, x minus I H k delta t, and then another x minus I H k delta t, and 0 here. So if we just stick the control operator into this corner, the derivative of the exponential with respect to that control operator coefficient magically pops out in the corner here. Now, because these matrices are very, very sparse, The cost of computing a Krylov exponential of this is just about twice the cost of just exponentiating, so the same cost as a finite difference test, but much better accuracy numerically. And also, you can see that when we are doing it, we get two things. We get the straight propagator, which will just propagate our system forward, and we get the derivative. So we are shooting two rabbits with one bullet in here. So this is the current way in which Spinach is calculating the propagator derivatives. On the strength of the fact that for the methods that provide machine precision accuracy assurances, this is by a longish mile the cheapest one out there. So we just create this composite matrix, Krylov exponentiated, and that's how the derivative is actually being computed. There are many other expressions of this type. So in particular, David's project is likely to revolve heavily around the expressions of this type, because higher derivatives is probably the most straightforward way to them. Because these series, I mean, you will encounter critical sums in there and so on. They will work. They might be useful for debugging and so on, and actually pay for themselves in the end. But that's certainly by considerable margin the fastest way of computing the things that I've ever seen. Okay, so next lecture I will take a look at the actual usage of these gradients once we got them. In principle, it's all already lectured and recorded. If you go into the quantum chemistry lecture and look at the lecture titled Molecular Geometry Optimization, I am going through each and every minimization method in there, from simplex all the way down to Newton and various regularizations of it. So in a way that's been done. And if there is a continued interest in these matters, I can give you the proper functional calculus version of this. So this is known as GRAPE. It's used in NMR. But the case where we don't actually discretize this CK and consider it as a functional variation problem with Lagrangian type formalisms is known as the Grotov method, developed in Russia and Israel chiefly. And it's useful for laser spectroscopy because in their case there's much more of a requirement for this to be a continuous function rather than a discrete sequence of slices. Okay, that's it for the lecture. Any questions?